Hi friends, we are going to learn asymptotic notations. These notations are very important. And what is this asymptotic notation is? Computer scientists used to compare more than one algorithm for the given problem. Their time complexity, or you can say order of growth for the larger set of input. I repeat, asymptotic notation is used by computer scientists to compare the order of growth or time complexity for different algorithm for the same given problem, right, with respect to larger size of input. We are not considering a smaller size of input. Always our concentration is, or we used to concentrate on larger size of input. So in this we are having big O notations, omega notations and theta notations. Big O is also, write it as a big O notations, omega notations and last is theta notations. Apart from this is there in your syllabus. Apart from this, there are two more notations, is a small o, that is called little o notations, and little omega notations. Little omega notations. Okay, so this is called little omega. This is called little o. So we'll be focused on these three notations: big O, big omega and theta notations with example. You can see that big O notation, omega notation, theta notations, and one by one you are going to perform the task. Now question is, what is big O notation? As I discussed in the definitions, we are going to compare two different algorithms for the largest size of input. So if I have two different algorithms, it means we are having two different time complexity or two different order of growth, right? And we are going to compare those and finding that which algorithm is having the higher order of growth. Fine. Big O notation is also used for, right, to represent worst case scenarios, worst case time complexity, while big omega is used for best case scenarios and theta is used for average case scenarios. So let us discuss first what is big omega. It will be better to go and discuss with example and graph. Let us see that this is x axis, we are talking about input size. Y axis we are talking about time complexity, right? For the given problem, maybe this is the one algorithms called having f of n, function of n, time complexity, while other algorithms has c into g of n. G of n is again function of n, c is a constant. Now we can see, anybody can observe out of these two graph, f of n and g of n, we can say that f of n is having higher order of growth than f of n. From where? Not from the beginning, from this cross sections point. So if we take this point, right, this call it as a n naught, and where n is a number of input. So we can say f of n is having lesser order of growth than g of n for all the values of n greater than equal to n naught, greater than equal to n naught. Then how to define this? We'll define it as function f of n is said to be in g of n only when function f of n is bounded above by g of n with constant multiple c, with constant multiple c. Mathematically, we can define as f of n is lesser than equal to c into g of n for all values of n greater than equal to n naught. And what is n naught? Where n is non-negative integer. N is non-negative integer. Then what about c? C is positive constant. As I mentioned, c is positive constant. So here friend, we can see that based on the diagrams, we can easily describe it. F of n is bounded above by function g of n with constant multiple c for all the values of n greater than n naught is definition of O notations. Now how to discuss example. Say we have given example is 100n plus 7. We don't know that what notation to be used, but we have taken this example for big O notations. It means if this is a f of n, then we have to find out g of n such a way that f of n will have lesser order of growth than g of n. So can we write this 100n plus 7 will be less than equal to 100n plus n. At the place of 7, 7 is a constant values. I am going to replace by function of n, that is a linear values. So this 7 is also part of linear, n is also linear. So we have converted this, or at the place of 7 you have written n such a way that right hand side parameter you can simplify it, and that will be in the function called g of n with constant multiple. So can we write this? 100n plus n is 101 n. Now our duty is to compare left and right parameters and find what is the minimum n naught values from where we can say f of n is having lesser order of growth than g of n. In that case, if we will take two example, here we have n, this side we have 100n plus 7 and right side we have 101n. 100n plus n is nothing but 101n, right? So we are going to simplify for the different values of n. If n is 0, this is a 7, this is 0. We cannot say that this value is lesser than 0, 7 is lesser than 0. No, it is wrong, right? So we have to fulfill this less than equal to. So this is wrong. Then we go for 1. 1 is nothing but it is 107. Right side it is 101. Still 107 is not lesser than 101. Wrong. Then we can go with 2. If we keeping 2 here, so 200 is 200, right? Plus 7. This side we have 101 into 2, 202. It is not correct. 3. We have 307. This side we have 303, not correct. Similarly, if you have 4, 407, this is 404, not correct. Then we have 5, 507, 505, not correct. 6, 607, here we have 606, not correct. If you have a 7, it is a 707, this is also 707, hence it is true. Let us take one more example. 8, we are getting 807, but this is what? 808, even it is true. It means this equations holds for all the values of n greater than equal to 7. Right? In that case, you can say that f of n is less than equal to c into g of n. And what is c, friend? C is here. C is equal to 101. What is n? N is greater than equal to 7. So this holds. Hence, we can say that. Hence, we can say that f of n belongs to big O of g of n. Remember, here we are not going to write. Here we are not going to write big O notation of c into g of n. No, we are not going to write c. Just to write f of n belongs to O of g of n. So, in the differentiations part we have discussed f of n is said to be g of n. We can simplify here and say that f of n belongs to big O of g of n. Right? So, this is all about big O notations. Similarly, there are little difference between both big omega notations. We need to think in a different way, or you can say in opposite way, but we are not going to write in exams like that. What is that? Again, we are going to take up one example. It is n, this is the input and this is the time complexity, and take this graph. Say this is c into g of n and this is f of n functions. Again, we are going to consider this part, just we are going to ignore, and we can write does not matter. This part does not matter for us. Always you are looking for the value of n greater than equal to n naught, which gives proper or satisfy proper equalities. So in this case, what is that? We can say that f of n is having higher order of growth than c into g of n. So we can write function f of n is said to be in g of n only when f of n is bounded below by function g of n with positive constant c, right? Mathematically, we can define as f of n is greater than equal to c into g of n. In DO notations, we have discussed f of n is lesser than equal to g of n. Here f of n is greater than equal to c into g of n, where c is positive constant and n must be greater than equal to, for all n must be greater than equal to n naught. And what is n naught? N naught is non-negative integer. Why non-negative integer? I am repeating it again and again. Not positive integer. Non-negative is what? You'll be thinking, why not? I can write positive integer. No, non-negative integer when you are talking, it is including 0 to positive integer. 0 is neither negative nor positive. But we can see that we have started from origin. There is a case for some examples, n will be greater than or equal to 0. So when you are talking about the positive integer, you start from 1, not from the 0. So we must write n is non-negative integer. It means positive integers along with value equal 0. In that case, we can say, hence, we can say that f of n belongs to omega of g of n. F of n belongs to omega of g of n. Now, to take some example to discuss omega notations, say f of n is 2x square plus 3. 2x square plus 3. This is f of n. Now, our tendency will be, or we can say 2n square, if it is a function of n, 2n square plus 3, because you are talking about function of n. Alright, we can take any example, but for this we have taken 2n square plus 3. No, what I said, our tendency is to make f of n greater than g of n. For that reason, can we write this 2n square plus 3 is greater than or equal to 2n square. Remember that g of n function must be from our order of growth what we have studied in the previous class, right? Maybe it will be n or log n square, n cube, 2 power n, n factorial. So we are going to simplify like that. It must fall in one of the basic efficiency class. We have written 2n square plus 3 greater than or equal to 2n square, but we need to justify it for what values of n. We need to find out n naught values, right? C is there, C is 2 here. What is C here? C is 2. What is g of n? G of n is n square. What we are looking for? N naught. So how we find out n naught values? We will apply the values again and again. So here we have 2n square plus 3 and here we have a 2n square. So if you are taking 0, it is 3, 0, it is true. If you are taking 1, it is 3 plus 2, 5, here is 2, it is true, because this is greater than or equal to, right? 2, it is 11, here 8, it is true. It means it is going to be true for all the values. Hence, we can say that n must be greater than or equal to 0. Hence, we can say 2n square plus n, or 2n square plus 3 belongs to 2n square plus 3 belongs to omega of big omega of n square. As I said, you don't write constant along with g of n, right? Or you can say f of n belongs to big omega of g of n. So this is all about your omega notations, and as I said, omega notation is used to note for best case efficiency. Now let us discuss for third case. And it's not like that whatever the example I am discussing, that is only last example. So you can take any examples. Our tendency is to prove it big omega, big O or theta notations. Now what is the theta notations? Theta notation, basically we are going to combine big O notations and big omega notations, and then we are going to define it in words. So it is n, it is input This is a time complexity. Say here we have a function. There is a second function here, right? F of n. This is g of n. Say one function over here is c2 g of n, right? And another is c1 g of n, right? c1 g of n. So we can see that basically when you are talking about the upper part, it looks like big O notations. F of n is lesser than c2 g of n. Bottom part, we can see that f of n is having higher order of growth than it is big omega notations. So big O notations, big omega notations, if we are going to combine, that will give you the theta notations. Now, remember that here we are getting one n values, this place, and you are getting another n values. So, since you have two scenarios, we will be getting two n values, n1 and n2. So, say this is n1, this is n2. So, we are going to consider for our reference is n2. How are we going to find? n0 must be max of n1 comma n2. n1 comma max of n1 comma n2. What are the values are greater? We'll take from thereafter only. This complete graph holds the properties of big omega and big O notations. So let us see how you are going to define it in the work. We are going to write f of n is said to be in function g of n only when f of n is bounded above and below by bounded above and below by function g of n with positive constant multiple c1 and c2 for all non-negative integer greater than equal to max of n1 comma n2. Mathematically we can define, see here bottom function is c1 g of n less than equal to f of n less than equal to c2 g of n. c1 g of n is less than equal to f of n less than equal to c2 g of n, right? For all n greater than equal to max of n1 comma n2. Then we can say, hence we can say that f of n belongs to theta of g of n. F of n belongs to theta of g of n, right? Now to discuss the example, say f of n is equal to n into n minus 1 divided by 2. Remember that here we need to find out two functions g of n. One should be greater than equal to f of n, other should be lesser than equal to f of n. So let us see. First, n into n minus 1 divided by 2. Can we simplify it? Yes. N square by 2 minus n by 2. We are subtracting some parameter out of first parameter. It means if you are going to ignore this, how it looks like? Can we say that it will be less than equal to n square by 2? Less than equal to, because you are ignoring this. Some amount you are subtracting, that you are ignoring it or removing it. It means overall n square by 2 holds larger values compared to n square by 2 minus n by 2. In that case, we are going to find for what values of n into n minus 1 by 2 is lesser than equal to n square by 2. For that, we can take n, we have n into n minus 1 divided by 2 and we have n square by 2. We will take the values one by one. 0, both are 0. 1, this side 0, this side 1 by 2. So 1 by 2 is greater, so it is true. Right? 0 in case it is both are equal, it is true. For 2, 2 into 2 minus 1 divided by 2 becomes 1. Here 2 square by 2, so it is 2, it is true. For 3, 3 square, 3 into 3 minus 1 divided by 2, it is 3. Right hand side 3 square, 9 by 2, 9 by 2, so 4.5, so it is true. So we can say that n into n minus 1 divided by 2 is less than equal to n square by 2, right, where c is equal to, can we write this? Can we write this as a 1 by 2? C is 1 by 2, and what about n? N is, n1 is greater than equal to 0, because it holds all the values from 0 to any values will take, n square by 2 is having larger values. So one parameter is done when we are saying f of n is lesser than g of n. So big O part is done. Okay. So let me go second part. So we can say that this is a C2 value. So this is also N2 values. Okay. This one is N2. Now second part, n into n minus 1 divided by 2. Can we simplify it? Yes, n square by 2 minus n by 2. Right. Now what is our tendency is to make this parameter greater than and equal to from the right hand side parameter. So what is our logic is, if you are subtracting 1 unit of n by 2 from this, it is n square by 2 minus n by 2, that is n into n minus 1 by 2. If you subtract 2 unit, what will happen? Let us see that n square by 2 minus n by 2 into n by 2. Can you simplify it? Yes. 2n square minus n square divided by 4. It is n square by 4. N square by 4. So we are going to write n into n minus 1 divided by 2 must be greater than equal to n square by 4. That will take an example. We will see that why you are adding greater than equal to. So in this case, we can see that we are having f of n function greater than g of n functions. In that case, we can see that c is what? 1 by 4. So it is C1 and N1 we need to find. How to find N1? Again we will go in the similar way. We have N into N minus 1 divided by 2, and here we have N square by 4. This is for your reference. We will take 0, 0, 0. We will take 1, it is 0. Right? This side 1 by 4. Look. Is n minus n by 2, 0 is greater than 1 by 4? No. It is 1 by 4 is fractional, 0.25. So it is not greater. So as cross marks. This was holding true. This is true, but this is wrong. Let us go for 2. 2 into 2 minus 1 divided by 2. It is 1. 2 square by 4. 4 by 4 is 1. It is true. Then go for 3. 3 into 3 minus 1 divided by 2 is 3. 3 into 3 minus 1 is 2, 2 divided by 2 is cancel, 3. 3 square, 9 divided by 4, it is going to be 2 point something, 2.25. Right? So still 3 is greater than this value. Even you can try for 4 and all, but we got that from n is equal to 2 onwards, values are giving proper indications that n into n minus 1 divided by 2 is having higher order of growth than n square by 4. So what is n1 values? From where it is continuous true values, because it is failed at n is equal to 1, so not consider it. From where it is true values, we will consider it. So n is equal to n1 is equal to 2. Once it is been done, then you are going to write it together. How are you going to write it together? First, lesser values can we write n square by 4 must be lesser than equal to n into n minus 1 divided by 2 must be less than equal to n square by 2. Let us see that how we are going to analyze it further. So here we have in n square by 4 less than equal to n into n minus 1 divided by 2 less than equal to n square by 2. C1 is 1 by 4. C2 is 1 by 2, G1n is n square, G2n is n square, while n is max of, look, n2 value was 0 and n1 is 2, 2 comma 0 is remain 2, so n must be greater than equal to 2. If it is, then we can say that, hence we can say n into n minus 1 divided by 2 belongs to theta of n square. N into n minus 1 divided by 2 belongs to theta of n square. So this is all about your asymptotic notations. I hope you understand difference between all three notations: big O, big omega and theta notations. And this conclusion is, it is useful for finding proper notations for the given efficiency class. While you are comparing it, always you are looking for that a particular basic efficiency class that we are going to find out based on asymptotic notations. Generally, for best case you are using big omega notations, for worst case you are using big O notations, and for average case scenarios theta notations. When you are in confusion also, you go and use theta notations because it's fall in both the sides omega as well as O notations. Thank you very much.